and just kind of mapped out what you're looking for on an NMR spectrum. And there's just a handful of zones there. The way you really get to be good at these is to do a bunch of examples, which we will do today. You try not to memorize charts like this, but they are good for kind of helping you keep track as you do specific examples. Okay, so that's two things that you're looking for as you look at a spectrum. We're onto a list of 4 total. First one is how many signals do you have? You just count them up. And the second one is where is it? Chemical shift left and right. So how many, where? All right, we'll finish off the list here very quickly. I think I'll keep this handy in case I need to point to that again, because there's one thing to know specifically about this aromatic zone region on a ring. And it kind of goes like this. On an aromatic ring, you have up to 6 hydrogens. And I'm just going to draw one of them. Remember, aromatic ring is what we draw looking like this. So it has double bonds kind of alternating all the way around it. And I'm just going to draw one of those hydrogens. So there's just one. Just one hydrogen. And what happens is you envision the external field, the magnetic field, coming in from this direction. Okay, here's the external field. Remember, we have decided that in order to do this at all, you've got to live inside a magnet. They're big. So there's what happens. You imagine that the magnetic field, so this one's external. It goes in this way, and this one is what the external field induces this one. So in other words, it's opposed to the external field. Now, it would be one thing if this new field that you created in the ring just went up in the other direction forever, but it doesn't. It's a loop. So it no more gets outside the ring, but what it turns around and wants to come back and go in a circle, which it does. So that by the time you get down to this other side of the ring here, it's made a complete loop. The ring itself is a ring. The external field, if it points this way, creates a new field that goes the other way because electrons circulate. And just look at the consequence for this one hydrogen right here. This one hydrogen, I have to be kind of wordy here, I'm afraid. It sits, say something like this, it sits in a spot where it now feels a higher, heads up there, a higher magnetic field than the one you put in. Okay? So that means it's now going to be definitely downfield. And here's just a quick little opportunity to refer that term to the spectrum itself. Remember, downfield means left. Upfield means right. Think of it as, actually you're changing the frequency, but think of it as changing the magnetic field strength, so you're cranking it up as you move left to right. A little bit stronger, until finally you get to where you flipped all of those protons. Well, what you've kind of done is the aromatics, which are, I don't know, I'm going to say 8.5 to 6.5. I've seen them that high. So that whole zone right there is where you can expect to see the aromatics. And the reason for that spot is that they have created their own little magnetic field that applies just on the ring itself. And so they feel both the external field and the internal field that they created for themselves. And that means that they're kind of in their own region, all by themselves. Now, that's the explanation. You won't have to do a lot of explaining anything like that, provided you kind of got it in your head. This number here, whoops, I'll get it on screen. That number right there, that's about as famous as 1700. Remember that from an infrared spectrum? 1700, 33,000, and so forth, the fence. There's a fence for you in an aromatic NMR spectrum. Okay, that's the one special place where you can expect to sort the whole universe into two different categories. Does it have an aromatic signal on it or not? That's kind of the big separation there. Okay, that's the list up through 2, and here are a couple of more quick ones. And here's what number 3 looks like. The relative area under the signal may be called the integral. This is just given to you. It may actually be printed on the spectrum sometimes. But you can't just look at a spectrum by itself and be able to tell what the area of a signal is. The instrument has a mathematical function that does it, and it's very quick at spitting it out for you. Okay, talk about how to use that. And then here's the next one. The splitting of each signal. Now we've counted them up. I'm going to say this is after you count the number of signals. Then it turns out that each one of those signals can be split. And it literally looks like somebody took a hatchet to a signal somewhere in the spectrum and just went whack, 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 and split it, literally. So that's why it got the name that it did. And there is one piece of information in the splitting, which is the number of hydrogens on neighboring carbons. Okay, and what I mean by that is, I'm going to do a real quick sketch here. Let's say that we're looking at this hydrogen right here, and on a neighboring carbon you have 2 hydrogens and everything else is not hydrogens. Okay, now you're looking at these. Those are the neighbors. All right, now you can start putting together pieces of molecules and sticking them together in some order that makes sense, which we'll do. And here is the handy rule that allows you to pick out the number of neighbors. So it goes like this. If you count your number of hydrogens on neighbor carbons, then you can expect the signal to get split into n+1 lines. Okay, and here's what that would look like. A doublet means just one neighbor hydrogen. A triplet, in other words, somebody took a hatchet and split the signal into 3 pieces. That means 2 neighbor hydrogens, and so forth. I'll just kind of stop with that because you can see the trend. All right, and we're going to use that. You probably won't learn a lot just by looking at the rule, but we'll use it. I'm going to say the reason for it is optional. You won't be quizzed on this, but I know for a fact that some of you like to have a few reasons so that you're not just memorizing, you kind of got a peg to hang your hat on here. The reason is that each one of the hydrogens that you see show up in a signal doesn't just sit all by itself. It has these neighbors, and each one of those is a little magnet too. Remember the little magnets I had up here on the screen to begin with? Okay, it turns out that each one of the neighbors has something to say about the strength that a magnetic hydrogen feels all on its own. So really, if you have just one neighbor hydrogen, you don't feel just one field. You feel one of your neighbors aligned with the external field and one of them against the external field. And those are the only two options. These are just for the neighbor hydrogens, remember, not for the hydrogen you are looking at. And then it gets more complicated from there, because if you're talking about 3 neighbor hydrogens, it could be like, well, here's one way to have them, and here's another way to have them, and here's another way to have them. Your neighbors have different ways of cooperating with or opposing the external field, and that makes the difference in the signal that you actually see. Like I mentioned, this is optional, so we won't spend much time on it. It's just a way of saying there's a good reason that we're about to see what we will. Okay, so we're going to put all this in motion here real quick. And let's do some examples, which I hope will look familiar. This is turning around and going back through the examples that we used just to do this, the number of signals. Now we're going to add layers onto it and pull it all together here. Okay, so this first one right here, number 1, number 2, number 3, and number 4. Okay, the number of signals. Okay, remember what we did before? Kind of gave each one its own letter if it was its own unique set. And there are 3 unique sets right there, A, B, and C, I think is what we call them. The splitting of each signal. Okay, now I'm going to, number of signals should be 3. Okay, so to begin with, I'll do this as a list format over here on the list, and I'm going to say A is some kind of splitting, and so is B, and so is C. But how about if we connect also to the structure itself, especially as we map the number of signals we should expect. Okay, number of signals in A, how many neighbors does it see? Okay, I'm going to give each one of these its own little label and kind of pull them out like this. Set A sees 2, I'll do this one all the way through and then you're going to start doing some with me, sees 2 neighbor hydrogens. So n plus 1 is 2 plus 1, which equals 3. A is a triplet. That one signal that is due to set A, yeah, it's one signal, but it is split into 3 little pieces. Next one. Now we're on set B. So you go, it sees, and here's kind of your first heads up example. If you go one way, you've got 1 neighbor carbon, and it has 2. If you go the other way, you've got a neighbor carbon that has 3, for a total of 5. This one sees 5 neighboring hydrogens. So this one, n plus 1, equals 5 plus 1, which equals 6. This one is a sextet, meaning 6. Split into 6 lines. Okay, the last one, number C. This one sees, what, 2 neighbors, and it's the hydrogens you're counting specifically, not just the number of carbons, and that means n plus 1 is equal to 2 plus 1, which equals 3. I'll come back to that point in just a minute. Triplet. There is your splitting that you predict. It's just a list. This signal will be split into this many lines. This signal will be split into this many lines. Here's the risk already up front. Some people will want to look at this one right here, C, and they'll go, oh, 3 hydrogens, so it should be a triplet. No. It's 3 lines not because there are 3 hydrogens in it. It's because there are 2 hydrogens next to it. That's maybe the most confusing thing to learn in interpreting a spectrum. It's not the number of hydrogens that make the signal, it's the number of hydrogens that are on neighboring carbons. I'll do several examples like that. Okay, the location of each signal. We can kind of map a little progression here, A, B, and C. This one will be, let's see, C will be the most upfield. This one will be the most downfield. And this one will be somewhere in the middle. Downfield, for the case of A, is due to the fact that it's near to that bromine. Okay, area under each signal, A, B, and C. Now here is where you do not look at the neighbors. You just look at the number of hydrogens that make the signal. A has 2, B also has 2, and C has 3. End of story. Now the actual numbers the spectrometer spits out at you may be 4 to 4 to 6 or something like that. But the ratio, as simple as you can get it in whole numbers, is 2 to 2 to 3. All right, and you could even sketch something like this. I won't do this for all of them, but let's just do a brief sketch. Let's see, somewhere around 4-ish to 1 should take care of all of it. So we would expect the most downfield to be A. So there's A, and here's B, and then somewhere, or sorry, here's C, and then somewhere in the middle is B. Okay, so your first one on the left should be a triplet. A is a triplet. And so you'd expect something like this. So there's a triplet. And then in the middle, there'd be this 6 line. So 1, 2, 3, 4, 5, 6. They can get kind of little and squished down near the baseline and hard to count and so forth, but that's what you'd have. So that one's a sextet. And the next one, the last one, which would be the farthest upfield, that's C, and it should just be 3 again. So something like that. Now, how do you use that? Well, you run the spectrum of the actual molecule, and if it really is this, you do see something like this. If you see something totally different, it's like, well, I didn't guess my structure right, I better adjust. That's the way you would use it in real life. Okay, first comprehensive example, all 4 things rolled together, even sketched into a spectrum like this. What questions do you have so far?
Is the area is equal to the number of hydrogens on each carbon?
It is. Mm-hmm. Okay, so let's do another one. Now I won't do quite so much elaborate mapping here. So let's go 1, 2, 3, and 4. We're predicting here. And remember, this one had no identical sets. They were all different from each other. So you kind of go A, B, C, D, and E. So there's your answer to the first one. You're going to expect 5 signals. Some of them may overlap, but that's okay. Now you do your prediction of splitting, which is probably the most important thing to do. And I won't do the full narrative here, but let's just do it sort of like this. This one sees 2 neighbors. It's split into a triplet. This one sees 3 neighbors. It's split into 4. This one sees 2 neighbors. It's split into 3. I should be boxing these. And almost done here. This last one sees 5 neighbors. That means you expect it to be split into 6 lines, and the last one sees 2 neighbors, so you expect it to be split into 3 lines. Okay, and this is the last time I'll list it all out. A is equal to a triplet. B is a quartet. C, triplet. And almost done. D is sextet. And E is a triplet. If you can count hydrogens and add one, you can do this. Okay, number 3, the location. I'm just going to draw a continuum here. You would expect A, we'll do this another way. Let's say B and C would be on the downfield side, and then somewhere in the middle you'd have D, and then you would have E and A upfield. Okay, so C somewhere in there. And this last one, number 4, the area under each signal. A would be 3, B and C and D would be 2, E would be 3. I won't sketch that one. I'm going to do this in abbreviated form on the next one. Remember, this one was mirror image, so it's nice and convenient to just go A, B, and C out from the middle. You could do it some other way if you wanted to. This will be more abbreviated now. C sees 2 hydrogens, so this will be a triplet. B sees 5 hydrogens, so it'll be a sextet. A sees 2 hydrogens. Let me break that off. So it's a triplet. Areas would be 2 to 2 to 3. Downfield, cleanly ranging up to the right as upfield, would go in that direction. Okay, that's starting to abbreviate it more, hopefully, as you kind of get into the groove. Okay, take a look at all of those, all 3 of them, and see what questions come to you after those. Seeing any patterns? Yeah, okay. Okay. You mean the number of neighbor hydrogens? Okay, so you're looking at, let me pick out B. You look at the number, all the neighbor carbons, there are 2. There's one on this side, one on that side. That one has 2. That one has 2. So that means that as B looks out, it sees a total of 4 neighbors. I'm sorry, 5, 3 and 2. 5 plus 1 is the 6 lines. So the neighbors are the next door carbons within the molecule itself. Help? Try this one right here. I'm going to cover this up. A, how many hydrogens does it see? How many neighbors? Well, it sees 1 neighbor carbon, but how many hydrogens are on that? 2. Yeah. You just move any direction you can to a neighbor, count the hydrogens. Okay, any more? That one was good. Okay, so let's do a few more. Now in a different view. We did several of these on Friday. They should look pretty familiar. And what you're looking at here now is the fact that there are no hydrogens shown. You've got to envision them according to what you know about the structure. And I guess we just go left to right here. Here's an A set, and here's a B set. And maybe the urge here is to forget, then on oxygen, how many hydrogens would there be on that oxygen? None. So you don't have to worry about it. Go to this next carbon right here. Yeah, there'd be some hydrogens there, a couple of them. And there's one here. And then these two, we said, are equivalent. All right, so the number of sets, you would expect 5 signals. And then you also need to look at splitting. So let's just do that right on the molecule itself. This one right here, I'm going to go back to an expanded version of this, sees 2 neighbors. So that means you expect to see 3 lines. It's a triplet. Okay, I may have to alternate in order to have enough room on this thing. This one, B, that one sees 3 neighbors. So you would expect that to be 4 lines, which equals a quartet. Okay, then we're to C. And this may be the one, I don't know, this one may be the trickiest one. Let's see how it goes. This one only has 1 neighbor. Just 1 neighbor hydrogen. So that means it is split into 2 lines, which equals a doublet. Then right down here in the middle, here's where it gets to be interesting to count. There is only 1 hydrogen right there. Okay, I think we're all okay with that. And it sits there and it makes its own signal. But look how many neighbors it's got. It's got 3 in this direction, and 3 in this direction, and 2 in that direction. That's 8. This one hydrogen here, right here, sees a total of 8 neighbor hydrogens. So it's 9 lines, and there is no official name for that. No net, I don't think that's even a word. So 9 lines, 8 plus 1. And then the last one, each one of these 2 is the same. E looks out at the world and it goes, I have 1 neighbor carbon. This E does the same thing. I just got 1 neighbor carbon. And so that means you go 1 plus 1. So he's 1 neighbor hydrogen. So it's a doublet, which is 1 plus 1. Questions on that?
2 each, right?
Yes.
1 line on the spectrum.
That's right. So let me say that also applies to this. This one statement applies to that. Now let's not forget step 3 though, which is the number of lines. The integrals. I forget which one. 3 was the location. I'm going to leave that undone for this one. Now let's look at the areas. A, B, C, D, and E. Okay, if there's any one trick here, it's just staying close enough to the structure that you don't miss. A is going to be 3, B will be 2, C will be 2, and then is when we kind of jump into territory that's tricky. You look at D, that one has to be 1, and E has to be what? Not 3, because there are 2 of those things. This one needs to be 6. Total of 6 hydrogens make up that signal from those 2 that are the same as each other. Okay, I'm going to do only part of the next one to give us time to do a little different stuff. The right-hand side, let me compare to the left-hand side. This one is the same as the previous one, so we don't need to put any time into that. The other side, though, has a terp-butyl group on it, and this one is amazingly simple. How many hydrogens are right here? Remember, there are none in that spot. And remember that all three of these are the same as each other. So let's call them all A. And so you're going to expect just one signal from it. And the splitting on this side is what? Well, each one of those methyl groups looks out at the world, and it's only got one spot it can look, which is that carbon right there. And how many hydrogens are there? None. So there is no splitting. And that means the signal you're actually going to observe is just one line. Singlet, and that's as simple as it gets. One line, nobody took a hatchet to it. Okay, take a look at those two. See what you might want to kind of probe in those. Yeah, Janae.
Can you show how you counted out the 8 neighbors?
The 8 for this one right here. Okay, so let me box this one so that it sticks right to that point. Okay, this one sees 6 here. Okay with that? Okay, and it sees one more here. No wonder you're confused. That should be 7, which should be 8. Does that make more sense?
Yeah.
Okay. It's not drawn. There's that one hydrogen right there. As long as you keep him in mind, 1 plus 6 is 7, add 1 to get 8. Now, the comparison here, since you raised this, is look out in this spot, no hydrogen there. Okay, what else? These have all been good. Okay, well, let's do one of these anyway, which we've already been through. Okay, this one, remember, had a mirror plane through the ring, and we said that that meant that we had 2 sets on the ring that were equivalent to each other, and then there would have been this little set right here all by itself. Okay, 3 signals. One for each of those sets, A, B, and C, and then the splitting. Okay, I'm just going to do that directly on the structure itself. A looks around and it goes, I'm looking to this neighbor, and there's a chlorine on it. No hydrogen, no splitting. But if I look at B, I see, yeah, I've got 1 hydrogen there. So this will be a doublet because it sees N plus 1 is 2, and the same goes for B. B is also a doublet because it looks around and it only sees 1 neighbor hydrogen. Remember? Sees just 1 neighbor hydrogen. And then the last splitting you're looking at is that set down there. And here's maybe an easy mistake to make. You may be going, well, this set right here, it looks at this carbon right here. No, actually it doesn't, because its only neighbor is an oxygen. That's the only neighbor of set C. So that means it's got no neighbor hydrogens. They don't even have any place to sit. It's a singlet. There is no splitting. Okay, questions on, I'm not going to try to do the whole thing. There's splitting. 3 and 4, we don't need to go through at this point. Okay, questions on that one? There is one thing that you could add to this, which is that A and B are definitely way downfield. C is less downfield. These are going to be like 7. C would be more like 4 parts per million. Okay, questions on that one? Counting the splitting is usually the hardest part. So if you're getting good at that, we can take the other step now. And I think we'll have time for just one of these, and then pick up some more in the future. All right, now you've got real options for structures, and you've got the actual spectrum. It has to be one of these. So let's figure out which one it is. And the quickest way in the world to do this is predict the number of signals that you ought to have out of each one of these compounds. And if it's not 2, then you don't have to worry with that one anymore. So let's do this. A, B, and C means that you should have 3 signals. A and B means that you should have 2 signals. And this next one, yeah, I'm afraid we're stuck with 4 here. There's A, B, C, and D there. Looking like that. And then, because there's a mirror plane right through the middle of this molecule, you'd expect A and B. 2 signals. Now, look at what you haven't done so far. You haven't tried to predict splitting. You haven't tried to decide upfield or downfield or anything like that. Just predict the number of signals. And what you've done is you've ruled out this one, and you've ruled out this one, because the main message out of this spectrum right here is that it has how many signals in it? Well, 2. There's one. Now it's split, into this little pile. And here's this one that's kind of big. But whatever the case may be, this one for sure has 2 signals, and that means it has to be either this one or this one. Okay, now if you kind of stop at that point, you wouldn't be too far off. What you'd do is you'd say, well, I'd expect in this one right here, which has 2 signals, I have 2 neighbors on that side, I have 2 neighbors on that side. Okay, so that one ought to be 5 lines in the middle. And this one right here, this one ought to be, well, it sees 3 on each side for a total of 6, so that ought to be 7 lines. And then you'd look at this middle pattern right here and you just go, yeah, that looks like it could be either 5 or 7. And you'd probably have to have a blow up of that region before you could really nail it. And then the other thing you'd need to do is carefully look at this signal right here, because that could be B here, or it could be B in this option right here. But what you want to look at is now the fact that if you compare these 2 options as the only ones that are left, you'd see that the bromine is on the middle carbon, and of these 2, A should be downfield, compared to its partners, versus this one up here, where A should be upfield of B. And it's pretty safe in both cases to say that we're looking at A and B. They're the same. You'd expect that out of either of those two options. Except that by looking at the details down here, you're saying, well, if it's A, that one should lie way to the left of its partners, versus this one right here, if it's A, that should be way to the right of its partners. And in fact, this one right here, A is definitely downfield compared to B. So that means you want to pick this one. Okay, now on purpose that was, kind of moving through it. So let's back up now and look at the first two steps. Are you okay with getting the number of signals out of each one? Forget where they are to begin with. Are you okay with getting 3 and 4 and saying it can't be either of those because it's 2? The next one requires you to know something about left and right. And that's how you make a call. Now, if that's the first one you've seen, which it is, are you going to make the jump to do all the rest of them easily and quickly? No, probably not. Take some practice, and we'll have some time for that as we go on. Let's do, I think we don't have time for any more. Let's just call it good right there. Do the problem set and call it a day. I'm going to give you the answer to number 3. Anybody still need one? They're coming that way. Okay, 3, we haven't quite made it as far as carbon 13 NMR in class yet. The answer to that one is 7. Okay, 1 and 2 are yours to do, and remember you're free to look at your notes or anything else you like. Okay, see you on Wednesday then. We'll pick up from there.